Good afternoon, everyone. The House of Sultan Chand Sons Private Limited extends a very warm welcome to all the participants to today's data science webinar. It feels nice to have you all here, and we thank you for that. A bit about the House first. We are pioneers in the field of book publishing in post-independence India, catering to students from pre-primary to university level, churning out over 600 regular titles besides adding new ones to our stable year after year. Known for competently written, elegantly produced, and reasonably priced books, our publications are widely prescribed in reputed schools and colleges across the nation, as well as in some neighboring countries. Our authors are distinguished academicians, professors, and educationists with vast experience and expertise. We are proud to be associated with them. I now introduce to you the host of today's webinar, Dr. Sachin Gupta. Besides being the author of 2 data science books for classes 9th and 10th, he is also Dean, Academics and Research, and Professor in the Department of Computer Science Engineering at MVNU for the past 7 years. He has also been HOD, Computer Science Engineering and MCA Department in Dronacharya Group of Institutions, Deputy Director and Head of the Computer Science Department in Chandraprabha Jain College of Higher Studies, affiliated to GGSIPU, Delhi. With a teaching experience of over 20 years, which includes teaching undergraduate and postgraduate students and researchers, Dr. Gupta's academic pursuits have been fairly meritorious, winning him several awards, distinctions, scholarships, including the Certificate of Academic Excellence by GGSIPU. Dr. Gupta has also contributed to various journals, conferences, and books for schools and higher education, both nationally and internationally. His achievements are commendable. May I now request the man himself to take you through today's session, Dr. Sachin Gupta. Have a great day ahead. Thank you.
A very good evening, everyone. Thank you so much for joining. Thank Manmohan sir for the very kind words that you have introduced me with. I hope I actually live up to the expectation. What the session today is, we are going to actually look at some statistical applications or how do we solve problems using data science. And this is the presentation that we are actually going to look at. I hope I am audible and visible. My screen is comfortably visible to everyone. If there are any queries during the session, we may please put them on the chat screen.
Yeah, you are audible and properly visible.
Okay, thank you so much, sir. Okay, so the topic for today is taken from chapter 2 of the class 10th book on data science. The chapter 2 deals particularly with 2 aspects. Part of it is probability that we are not discussing today, but part of it is actually the statistical problem solving method. I took this opportunity to actually add in some more concept beyond the book also, because I believe that most of the people cannot make a correlation between how statistics is actually converging to data science, or how data science actually plays a role eventually in AI, or how AI models actually are used in machine learning and deep learning and so forth. So for all of them, the basic requirement is that we are actually starting out with some process that is actually the statistical problem solving method, and that we will see today with the demonstration as well. So welcome to the knowledge series on data science, and Christmas greetings to everyone who has joined today. It's the eve of Christmas. Fortunately, a very nice day to actually have people around to speak. I am a computer science faculty. I've been struggling with information technology since the last 20 years, but fortunately, I'm yet to give up. So I consider that as a win. I actually wrote 2 books so far on essentials of data science, one for class 10th, one for class 9th, and my publishers have been very gracious to have brought that out. They've been a good time and absolutely excellent books. I'm also working as a product advisor AI at methodai.com, where I actually keep exploring more, learning from corporate, so much data to work with. We are going to discuss today is what is problem solving, basically, how do humans solve problem. Then statistical problem solving method, demonstration on CODAP, and some questions which you may ask later. So there are some terms which you might already know. If you are joining in now, I can actually seek if somebody wants to send some input. What is the problem solving process? What is variability in data? This is one of the most important questions which I have come across in statistics. One of the least asked questions also. What is variability, or why do we actually have to think about variability? Then what is correlation? Then is data science related to stats, or is data science related to artificial intelligence as well? So these are some of the basic questions that we intend to answer. So first thing first, what is the human problem solving process? We essentially describe the problem at the first stage, that I may be able to put it in a normal English language. I may write a structured query language query. I may be writing anyhow that some way I would like to actually describe the problem, that this is what I want to do. Secondly, with every problem, we also describe that what are the results that we want to actually get. This allows us to formulate a question. We will demonstrate it with something later on. But for the time being, the sufficient information is that we describe the problem, we describe the results that we want out of it, and then we start gathering information which can actually answer the question that we have raised. Sometimes we may have all the information that we need, sometimes we may have absolutely zero information, but without information, we will not be able to answer the question that we formulated during the problem statement. After gathering information, we try to think of some solution based on the information that we have gathered. We choose or optimize the solutions to the best possible optimal solution. And sometimes we have to implement it if we are thinking about a computer generated program for implementing a solution. And eventually we try to evaluate the results that are associated with it. After evaluating the results, there we have several possibilities, but maybe the result that we got were surprising. Maybe the question that we formulated was not actually appropriate. So we may go back to the stage of formulating a question again, or maybe the answers we are getting require more information to be gathered. That means the information which we collected was not complete, that we found some new additional constraint, so we might need to gather more information. Even after evaluating, it might be possible that we come to see some solution that we haven't even thought earlier. So in these cases, we might think of more solutions after evaluating the result, or the choice of my best solution may become different with the evaluation. Even at times that my prototype for the program that we developed, that might actually be required to change. So we may implement the solution again with the help of the result. That means my results were, let us say, only 80% accurate, and I wanted to make them better. So I may actually be able to make them better by evaluating, then implementing the solution differently, and that might make my results better. So this is a spiral, and we can enter the spiral at any stage of the process. Stage 2, 3, 4, 5, 6. I may actually change any of the stages. And this is the normal human problem solving process that we usually discuss. Comparatively, the statistical problem solving process is just a 4-stage, but there is a lot of feedback again. So from the previous page, we are actually looking at formulation of a statistical or investigative question. Now, this part is important. So in this phase, we said there is a problem and we want the results that to be defined prior, and then we formulate a question. In the statistical problem solving process, we have to formulate a statistical question. And this actually relies too much on a one part that we call as variability. So we are going to discuss what variability is. When do we call a question as a statistical investigative question? That is actually a requirement. At the next stage, we consider collect the data. Then we analyze the data. Then we interpret the result. From the data collection phase, we can go back to changing our question. From the analysis of the data, we can go back to our investigative question again. Or from analysis, we can go back to collecting more data. And from interpreting the results, again, it can take back us to the formulation of our question or to the collection of the data back. This is the normal statistical problem solving process. So in the beginning, we spoke about that. How is data associated with other streams? I mean, when we talk about artificial intelligence or machine learning or data science, does data play any role there? That is a question that we usually ask. So the very basic flow of how AI works is that whenever we are using artificial intelligence, we are heavily dependent on data. That means unless and until we have got a good quality of data, we would not be able to actually create any value out of artificial intelligence. So artificial intelligence algorithms allow us to make good use of data and create a value from this data. That's the basic flow. Okay. So you may wonder there that what kind of data that would be actually domain specific, not necessarily that which data are we actually looking to. Then we may also wonder that what is the, just a moment. Okay, I just wanted to see my chat quickly. Okay, so the second question is that if in case we have a lot of data and all of the data is almost consistently constant, would AI be able to give me some value? The answer is no. So the one part that actually pertains to my first question in statistical analysis that we spoke about was that I need to understand that the data, there must be some variability in the data. The same rule goes for artificial intelligence. If my data is coming from varied sources and it has a lot of variability, then only artificial intelligence algorithms will be able to learn from this data, otherwise not. And then I have to consider some value. Let us break this basic flow into more. Let us break it into bigger flow. So when we speak about statistics part, we are speaking about only the first box, that we have some data. We use statistics for selecting or collecting the data. That means I may have a large collection of data. I may choose some part of it that you call as sampling usually, or I may actually have to gather the data if I don't have any data. And from this, we go to analysis. Statistics also deals with interpretation of data and so forth. So this is the only part, that first part, that deals about data alone. Now, coming to artificial intelligence, we may say this is a combination of two things. Part of AI is data science and part of AI is modeling of the data. So the part of AI that deals with data science, that says that whatever data that we had, whatever variable data that we had, the data we collected, it might not be appropriate or it might not be good enough for my AI model to be able to consume. So what data science does is, data science allows us to explore the data, looking for some patterns if they are already existing and that we can see. It allows us to clean the data. Cleaning means there may be some empty value, there may be some extrapolated value, there may be some values which are not possible in the data. Like in a phone number, there is a name, or in the name column, there is some number. Then we normalize the data. We make the features compatible with each other. I mean, it may be possible that I have to take the logarithm of a feature because it was too big. I may have to square or cube some feature because it was too small, or I have to combine some features together. That part we call as feature engineering. And eventually we scale. So whatever data that we had from the statistical collection of data, from my problem statement, data science helps us to actually understand the semantic of data, check out that the data is good. If the data is bad, then make it clean, normalize it, make it good for consumption in the next phase that we call as the modeling. So within AI, we actually create a model, we select a model, then train the model, evaluate it, and then tune it again. So in this complete process, this training phase is very, very critical. And this actually depends heavily on what is the quality of data that we are receiving through the data science. And this in turn actually deals with what is the type of question that we formulated during the statistical investigative process. So anything, any value that we want to derive from artificial intelligence can be used to make an operational software. We can deploy it, we can keep monitoring our code, and we can retrain the model as and when required, whenever the needs arises. I mean, that may be possible that different kind of people or different kind of data is coming. So in that case, we may have to retrain the model as well. So the short summary of my question here is that whenever I have generated value from the data, it would always depend on what kind of modeling we are doing. How do we train our AI model? Then this training in turn depends heavily on my data science process, that how am I actually going to be able to clean the data or make it suitable enough for my model to consume. And this depends on the statistical problem solving process. So statistics, all in all, is the bedrock of all data related evaluation process, be it AI, be it ML, be it data science. For all of them, the statistics or the statistical problem solving method actually works. Let me take a quick look at the chat if in case there is any question that somebody might have had. Okay, so no questions here so far. Gladly. Let us move ahead. So what we are going to discuss today, we'll demonstrate a small case study where how are you going to decide that if in case you are going to a shopping mall or a supermarket, then how do they decide that how many number of lanes should be there for the customers? Because this actually translates to a problem. Problem is that I may have a lot of lanes for checkout. Then I have to put in enough point of service or point of sales machines. I have to actually bring in a lot of sales people also in that process. And for all of this, I require to spend money. So if I have got too many people coming in and my lanes are less, then I have a problem. But if I have too few people coming and my lanes are more, then I'm actually spending a lot of money doing nothing. So that's not productive. So we have to consider this from a statistical perspective. My problem is from a real domain. So this can be applied to your metro lines. This can be applied to your stadium entry. This can be applied to anywhere where there is a queuing requirement, that how many number of queues should you open in case this is the amount of people coming in for entry or for checkout. Okay. So in networking, we call it the queuing theory. In statistics, we are actually looking at that. Should there be a correlation between the number of lanes versus the waiting time? So my problem statement is very clear that we are looking to find out that is there a relationship existing between the number of lanes on one hand and the average waiting time on the other hand. All right. We are going to look at it through the lens of CODAP. CODAP is a tool that we are using on our platform, methodai.com. So methodai.com is basically a tech platform for artificial intelligence, data science, and statistics. And we have just introduced CODAP on this, where you'd be able to see a lot of problems that we are taking in from real life domain and bringing it to data science and statistics, making it easier for every student to learn. through visual analysis of the data. So let's jump into the problem again. So this is my basic problem statement. I'll start with each of the things one by one. So the first thing is, we defined a problem statement that was very clear. We said that is there any correlation or is there any relationship existing between the number of lines that are available for checkout versus what is the waiting time they have to see. So the store owner of a very popular store actually wanted to solve this problem, right? And he asked us that how can you ensure that we have an optimal number of lanes depending on there are a lot of factors. What we asked him essentially was, we asked him to collect the data. So we asked him to, for a sample, keep 2 checkout lanes, calculate what is the average waiting time of each of the customer in minutes. Okay. Then do the same activity for different days of the week. That means we wanted to see that it may be possible that on some days we have more lanes, on some days we have less number of lanes. So we work with every day of the week, Tuesday, Friday, Thursday, Wednesday, Monday, randomly. Okay. We also wanted to see that at which hour of the day, what is the total number of customers that we were getting. That means since the store opened at 8 a.m. to the store closing time at 8 p.m. we wanted to check, or 5 p.m. we wanted to check out that what is the number of customers we were waiting in the queue and what was the average waiting time they had. We also took into consideration what was the size of the store, and this is fixed as of now because data is coming from a single source. That means the store was 20,000 square feet in size. And then we wanted to know what is the customer count at each time. At 8 a.m., what was the customer count? Then on Thursday, 8 a.m., what was the customer count? Then on Wednesday, 12 p.m., what was the customer count, and so forth. So this is the kind of data that we are actually looking forward for my statistical problem solving analysis, that we wanted the concerned person who wanted to actually check out that in the supermarket that how many lanes are going to be necessary to be implemented. All right. Any questions so far? Nothing? No question. Thank you so much. Any questions on the, okay, Ashish said just share any questions. Okay, fine. No questions. All right. So understanding the data part is convenient. Now, my second question comes into picture. Is there variability? I mean, are the number of lanes going to be different? So if we keep on only 2 checkout lanes, there's no variability, but we wanted to see variable data. So on some days, we kept in 3 checkout lanes. On some days, we kept in 4 checkout lanes. On some other days, we kept 5 checkout lanes open. On yet some other days, we kept 6 checkout lanes open and so forth. So there is definitely variability in the checkout lanes. Then what I wanted, my question was that can we reduce the average waiting time if we increase the number of checkout lanes or vice versa? So is that average waiting time variable? Yes, the average waiting time is also variable, as you can see from the data. So this variability is important because this is something that we need, that our algorithms learn from. So because our algorithm comes to see that there are different responses. Had there been a constant waiting time for all the customers in every scenario, then this statistical question would have had no meaning. So going back to my presentation, I spoke about that variability is one of the key components whenever you are actually trying to formulate a statistical question. Then, by common sense, you would be able to realize that there may be more shoppers on Sunday instead of a Monday. Because the people are, if it is a grocery store, that people actually do grocery shopping on weekend, then there would be more people on Sunday as compared to a working day like a Monday or a Tuesday. Similarly, there is a variability on the hour of the day. There may be more customers at peak hours and there may be less customers at non-peak hours of the day. So that is again a variable portion. Store size is fixed. So we cannot answer any statistical questions on the base of the store size, but the customer count is again variable. So there is a lot of variability in the data, and this is a good data set which can be actually used in both artificial intelligence, machine learning, and for statistical analysis as well. Right? We have just taken 46 cases, but in a real life scenario, this data would be actually going across like on highways when on Delhi-Palwal route, they wanted to set up a toll. So how do they decide the number of lanes in the toll? That was heavily dependent on. So they conduct a survey for almost 2 months prior, where they see that what is the number of vehicles passing through the toll or that road on all the times of the day. So that survey is very important. There they get to see that if there were some checkout lane, then they simulate a scenario with 2, 3, 4 multiple checkout lanes or multiple toll lanes, and then seek that what would be the average time. So that is a practical real life scenario, but that would require you to have far more than 46. That may be actually roughly, say, a couple of lakhs entries where we can see the patterns emerging from our data. So that is the beauty of data. So we want to see that is there a relationship existing between the checkout length and the average waiting time minute. So let me go back quickly to my presentation for a while, and let us define the coefficient of correlation and see the direction of it as well. So coefficient of correlation between two variables usually tells that if the R value is exactly 1, that means they are perfectly correlated with each other. That means that when one variable increases, the other variable also increases. That means if I increase the number of lanes, the average waiting time should also increase. That's not the case here, but I'm just actually giving for an example that if you increase the purchase, then the number of sales also is going to increase. There is a perfect correlation between them. So the R value can be ranging between -1 to +1. For +1, it's a perfect correlation. For -1, it's also a perfect correlation, but a perfect negative correlation. So this is the positive correlation. If in the graph shows something like this, there is a negative correlation. If the graph is close to -1, there is a strong association. If R is close to 1, that means from 0, the closer I get to 1, there is a close correlation happening between the two values that we are trying to find out. And if it is closing to -1, that there is a negative correlation. By instinct, you may be able to actually understand that if I increase the number of lanes, ideally the waiting time should decrease because there are more lanes. The people would actually have to wait less. So by default, that this is our understanding. Let us see with data whether it's actually true or not. At some times, R is close to 0. If there is no association between the two variables, then we can say there is the coefficient of correlation would be 0. Let us now try to find out that what kind of correlation exists between our two variables that we want to see. So my variables are, I want to see how many number of checkout lane. I want to see what is the average time in minutes. Okay. So let us create a graph that is actually plotting. On the one hand, there are checkout lanes, and on the other hand, there is average waiting time in minutes. Right. This would be the graph that we are actually getting out of the data that we have just used. Going back to how do we find out what is the correlation between them? Let us check out. So looking at the graph, there is an equation that we can actually see that the average waiting time versus the checkout lane, the correlation value is 0.855, right? It's a negative correlation as shown by the direction of the graph. But at the same time, we are seeing there is a pretty close correlation between the two values. That means if I keep on increasing the checkout lane, the average waiting time should keep on decreasing, and vice versa. If my checkout lanes are going to be less, that means for 2 lanes checkout, the waiting times were more than 8 minutes on the average. For 3 lanes, the waiting time reduced to roughly close to 7 or less. For 4 lanes, the waiting time reduced to even more, 6 or less. For 5 lanes was lesser. For 4 lanes, it was again lesser, and so forth. All right. So for the average time, waiting time was actually reduced to 5 minutes or 4 minutes or 6 minutes, depending on if we keep on increasing the number of checkout lanes. So we ran the model only up to 6 lanes in the data, as you can see. So that is the correlation existing between this. So we can see that with this equation, we'll be able to comfortably calculate that what would be the average waiting time in case the number of lanes is given fixed, right? So we can project it also. If I wanted to find out what is the value for 7 lanes, I would just substitute the equation with minus 0.95 into 7 plus 10.05, and that would give me the average waiting time for 7 lanes as well. I can picture it for 8, 9, 10 or any number of lanes that would actually work. So this is one part of my data analysis. Then we also want to see that does the customer count actually affects my data also. So there is a second graph that we are actually looking at. So this actually plots the number of checkout lanes again, 0, 1, 2, 3, 4, 5, 6, 7. And the customer count that for 200 customers up to 380 total customers, how does it affect my average waiting time? So my graph is actually check out that for 2 lanes, the average waiting time is ranging between 8 to 9.5 minutes. Okay. For 3 lanes, the average waiting time is ranging between 6.5 to 8 minutes. For 3 lanes, the average waiting time is between 5.5 to 6.5. But increasing the number of customers is actually increasing the waiting time as well. All right. Then between 5 to 5.5 minutes for 4 checkout lanes. But I have to also see that the time actually increased towards 5.5 when my customers went from 300 to 300 plus. And lastly, the time for checkout lane, number of checkout lanes 5 or above, the average waiting time is between 4.5 to 5 minutes. Right. So this is again another thing that there are 2 variables which can actually affect my number of lanes. One of them being that what is the total number of customers that we have in the store at any point of time. And second is that what is the total number of checkout lanes. So we can see that there would always be a correlation between the number of customers to the waiting time and the number of checkout lanes to the waiting time. So there may be more parameters. We have not actually simulated it as per the day of the week or hour of the day or more parameters. But then comes my more question. So yet another question comes in. The second question was, is there variability? What is causing the variability? So hour of the day is causing the variability. Then day of the week is also causing the variability. Then the customer count is also causing the variability in the average waiting time and the number of lanes. So all of them are. Then we explored the relationship between checkout lanes and waiting time. We also saw that because the customer count is also variable and hour of the day is variable, so this is something that we have to figure it out in our statistical exploration. There are more relationships. There may be more data needed. So this is just an example of a statistical problem solving method where we could actually try and find out that is there any possibility of understanding or using statistics to design the number of lanes in our example for statistical analysis of data. All right. So this is something that we have actually discovered. Yes, there is variable. Wherever there is variability, wherever there is data, we can apply a statistical problem solving method. go back to our slides and check out that what were the steps that we were to follow. So we created investigative statistical question that is it possible to reduce the waiting time by increasing the number of lanes? Yes, that question can be answered only after collecting and considering the data. Then we had to analyze the data to see what was the correlation. Then we saw there was the equation. We interpreted the result based on the coefficient of correlation. And then we actually went back to collect more data because there was a lot of number of customers, or there was day of the week considerations also, or hour of the day consideration also, that could actually make more analysis and interpret more result. And eventually my statistical question is going to be able to be answered, right? So that's about for the statistical analysis process in detail. I am opening the floor for questions if there are any, before we close the session.
A big thank you, Dr. Gupta, for today's interesting and informative session.
Thank you so much, sir.
Yeah, I'm sure the participants must have been benefited a lot by your talk. Since this is a series of webinars, we'll let you know about the next sessions well in advance. Merry Christmas and a Happy New Year, everyone. Stay safe. Thank you.
Thank you so much.